So let's start with the hands-on session of today. Luckily, we will be trying to work. I hope all of you managed to install this tool, EasyFermi, and that you managed to run it. If not, well, we are a lot of people, so I cannot guarantee that we can solve each of your troubles. But today, at least, we count with one of the experts in EasyFermi, Douglas, that is sitting here. And he will be showing us how to make a Fermilat analysis with this interface, which is actually pretty easy to use. That's the name of it. It's not the official Fermilat analysis tool, but it's based on all the official Fermi tools, and it's based on Python, etc., etc. But it's pretty straightforward and very friendly to use. And I think that for this hands-on session, and for you to get a little first touch with gamma ray analysis is nice. Or at least you can get the idea. And the cool thing about EasyFermi, well, we shared some share folder with you with some data, and you also have this presentation there, the presentation by Douglas, and you will see that there are several links. And for example, EasyFermi have some YouTube tutorials that you can follow at home if you are more interested, and so. And why did we choose, or why did we thought about using Fermi and not anything else? Well, because Fermilat data, all of the data is public, so you can really access all of the data set that they have been taking since 2008, so that's almost 15 years of data. And so if you're interested, you can always go, download your data, analyze it, and publish a paper, okay? So that's the good thing about Fermilat. As I was mentioning in my talks, the problem with Cherenkov telescopes is that the data is proprietary to the people in the collaboration. We admit now external collaborators to submit proposals. So once a year, when we operate our call, you can contact the Magic collaboration and you can submit a proposal. But you need to be in touch with one of the members. And I think that for HES and Veritas, it's the same procedure indeed. But in this case, if you get your proposal approved, you would only be guaranteed to access your own data, okay? However, we will see that some of the published results are available in FITS formats, and you can access to them in case you are interested in some of these. CTA will be open. Right now there is no data because there is no observatory, but the tools that we will use are there, and you can indeed use them to analyze some simulations, and you can also use the tools that we have developed in CTA to even analyze some of these data here. And the same goes for LASSO and all of these detectors that the data is not public. So just really short. Cherenkov telescopes, we use all of our analysis are based on root and C. You know that root is what is used at CERN, and as I said, all of our data is internal, but we have some public data available. And if you access this presentation that we share with you, you can see, for example, wait, no? No, I thought I could, wait, I could click in here, but do you see the mouse? No. It's not there, no? Give me 1 second, please. Let me see if sharing if with the PDF we can see it. No, you cannot see, okay? So give me another second. No? Okay. Okay, nothing. Okay, so let's try again. Do you see the mouse somewhere? Yes, here, no? Okay. So, well, of course it's not working. Okay, but if you were to click in here, you would get access to all of the websites where you can actually find the public data that has been released already. So this is the result of publications, okay? And all of these data are in what we call this DL3 format. Which is it's the way that we are moving from Cherenkov telescopes to try to go to something more standardized. So we are able to combine the data, and so you are able to analyze it with Python, etc., etc. And okay, I will just stay here, I think, today. And yeah, well, so this is what I was saying, no? So basically, right now we are moving from this to here, and CTA indeed will be based on Python. And right now there are two tools that are used to analyze this data. GammaPy, that will be the official package to analyze CTA's data, and CTools that was also developed at the same time and that you can actually use too. And if you access to these two links here that I put, that are not opening, of course, neither, you will get access to it. The good thing is that, for example, if you come to GammaPy, let's see if I can maybe share it from here. Give me again 1 second. Mira la página. Okay. So if I click there where you see GammaPy, okay. Sorry guys, this is not and now of course my computer froze. Okay, so maybe we can skip this thing and then just move to the hands-on properly. Okay. Uh, so. So it was a bit, when deciding what to do today, it was a little bit complicated to maybe try to analyze some Cherenkov data. So we decided to do the Fermilab analysis. And if you continue the presentation and we go down, okay, it's not working at all. And if you continue checking these slides, you will see that there are some links. No. Okay, well. Okay, if you continue and check these slides, here you will have access to the official website where you can check all of the data access of Fermilab. There you have all of the tutorials to do the official analysis of Fermilab, okay, with the so-called Fermi tools, etc., etc. You have step-by-step guidelines. And even we put in here some interesting pages that you can check. For example, Fermilab is monitoring bright sources. So you can go to this first link that we put in here, and you can check which the daily light curves for many sources, and you can see which of them are flaring, and then you can say, okay, I'm interested in this source, I will download this data, I will analyze it. And then there is also this thing called the light curve repository, where you actually, when you enter, you can see. Let's try again. I'm still positive, but let's see. Okay, now I come here, and let's see if it opens. Ah, it's opening, yes. Okay. So, and this Fermi light curve repository, you will be able to see the Fermi sky, and at some point it should appear here, okay? And you will actually see the different sources that Fermi has detected and with high significance. Look, nice. So this is interesting in the case that, for example, the data is loading, but you will see a lot of points in here right now. You can select your favorite source when it's finished loading, okay? And you can actually download a light curve, okay? And you can so this is like data already analyzed, okay, that you can download and you can use for whatever you want. You can come here. Okay. I cannot see very well, sorry. Well, once you select your source, okay, you will have a tab here where you can download all of this data and use it, okay? Yeah, and it's data already reduced. But okay, let's try to go back to the presentation. Okay, forget the presentation. So all of this you can access in these slides here. But as I said, today we will be using Easy Fermi. Okay, you were sent the instructions. You also took some pictures to what I said. This was this tool that was developed here in Brazil. I think here in Sao Paulo, no, by Ranieri de Menezes. And yeah, as I said, it's not the official tool, but it's pretty straightforward to use. And there you have a lot of links of how to access the Easy Fermi information. And yeah, we have Douglas that maybe come here, and since he's the expert of Easy Fermi, he will be showing how to do the analysis. Maybe this. No. And in this PDF that I share with you also, at the very end, you have other stuff to play with, and you will see two websites. That one points to Veritas. It was the Veritas collaboration designed the Muon Hunter. It's a kind of a game, something similar to what Irene was telling the other day about gravitational waves, in which you could help identifying these shapes that they saw. Veritas did the same for muons. We also record in our cameras muons that they like rings, and you can help Veritas identifying these muons, okay? And there is also a tool that was developed by some colleagues in Magic where you can actually enter and be like a magic analyzer and understand how to run some data. But okay, let's go with the Easy Fermi. Okay, so.
Okay, so hi everyone. Let me ask, who has Anaconda already installed or Miniconda? Raise your hand, please. All right, it's really gonna speed things up. Okay, so I thought it wasn't a must, but yeah, Miniconda is a must-have to install Fermi tools. It's very important. I didn't found any other way to install Fermi tools, and Easy Fermi relies solely on Fermi tools and not on FermiPy as I previously thought. So right, the first step. Let's see how we set up Easy Fermi. I sent you, Raul sent you the link for a Google Drive where you have these instructions and some other files that I'll ask you to download. And yeah, these are the instructions to install Easy Fermi. They're pretty straightforward. If you have Conda, you need to create an environment. That's the first line. If you create an environment, Conda already manages all the dependencies for you, so you don't have to worry about conflicts of different requirements. But some people were having a problem where by doing that first line, the Fermi tools was not installing correctly. So if you have did someone have that problem where they try to do this? Yeah, I see some people had that problem. He asks for, it says the module pi likelihood wasn't installed correctly, I think. So if you have the problem, try to run the environment without those air quotes. I think that might be the problem, but well. All right, let's see the next step. Has anyone already did the first line? Who's already passed the first step? Raise your hand. Oh, you had a problem? It says pi likelihood not found, the module. Yeah, I think the problem with that is that maybe the air quotes are in some systems that doesn't work. So maybe try creating the environment without the air quotes. Uh, it's possible to. Uh, I send you the link. I send the link in the WhatsApp group for like the instructions to install Fermi tools in case this doesn't work. So hopefully we can get around it. That we can get around the problem by looking at the GitHub page for Fermi tools. But okay. So let me ask again: who has passed the first line, the first test? Not a lot of people. So okay, what seems to be the problem? Are you guys having problems with the first line? The first, it's running. Yeah, it takes a while. It needs to install a lot of stuff. Sure. Is it? I don't know. In the GitHub, they tell you if you have problems with Conda, maybe use Mamba. You see on the link for the GitHub page of Permitools. So maybe try to do that. I hope it works. I haven't tested myself, but I hope it works. Okay. I don't know. We'll wait. I guess we'll wait for people to install. It takes a while to set up the environment. You have to download a lot of packages, and Condom has to make sure everything's working. But once you do that, hopefully you install everything, and then you can just once you create the environment, that's what the first line does. You can activate the environment and get into it by using that second line. You activate the environment called Fermi, and once you do that, you can just install. You can just run the last line with to install and get easy Fermi. Uh, does anyone manage to install with Mamba? Yeah. Did you manage to do it? No problem? Did you find any problems? Okay, that's good to know. Is Mamba like Conda? Can you just like create environments on the same? Is it better? Oh, I didn't know that. Okay, that's good to know. So that's one thing you guys can use Mamba if you have problems apparently. Uh, and okay, let me ask another question. Dija, if is it just can you just replace like the Conda commands with Mamba? Okay, so yeah, if you keep having problems with Conda, I'm sorry. So you can use Mamba maybe, and I think the commands will be very analogous. Just change Conda to Mamba when it comes to doing stuff. All right, let's see here.
You want to mention that?
Uh, well, while you guys do that, I guess I'll talk a bit about Easy Fermi. It was developed by a friend from my research group, which is Ranieri. He's very talented. He likes a lot about. He's very involved with Fermi. And uh, if you guys want to know more about Easy Fermi and maybe report bugs because it's a quite new tool and it has quite a bunch of bugs. Uh, then just go to the GitHub and annoy the hell out of them until some of these bugs are fixed. Okay. Uh, this is really difficult. All right, I'm gonna ask again. Did you guys manage the first line now? I see more hands, but still we have problems here. Oh, it's going. Yeah, it takes a while to set up the environment. I guess we'll wait a bit more. Let Let's see what else what I can talk about. Oh my god, it's difficult. Uh, all right. No. Uh, yeah, everyone decided to install it on the last minute. That might be a problem, the bandwidth. But just so I don't sit here and not say anything, let me show you that. Again, Raul has shared with you a link to a Google Drive called Easy for Me Tutor, and you'll find the slides, my slides, and Alicia's slides here if you have any questions. And here it's the target that I want to focus here on this hands-on session, which is Blazar PKS something something. And you find this text file. It's this one right here. It contains like some information, basic information about the source, and some utilities about Fermi that you might want to know. For example, let's see here. Where am I? Oh boy, this is difficult. All right, here we are. All right, so I cannot see from here.
It's not easy.
Can you read it? It's difficult, yeah. Well, but if you go to the folder, you find this txt file. It has some. Sorry. I did not hear. How do I do that?
Not just
Yeah,
to see.
help me out here real quick. Oh, it's because I can't see from over here. Yeah, that's the problem. Yeah, that's right. Yeah, maybe if you could turn off these lights, that would help a bit. All right, that's better. Ah, there we go. All right, so what do you have? There are some support links. When you go to, as Alicia said, Fermi data is public, so anyone can have access to it. Up there is a link where you can go to query for Fermi data. So let me show you what that looks like. It's right here. If you grab, I believe, the first link, you get to this page, and you can just fill it up with whatever source you want, maybe the name or the coordinates. And then you have to put in the observation dates, the time period you want to look at it, and the energy range that you want to look for, that you want to study. I have examples of this in my slides. Let me just go back. Oh boy, this is.
Yeah, and for example, you can check the tool I was telling you about the bright sources, that it's the link, it's in the presentation I sent. You can select, and then you can query the data according to where you are interested.
Yeah. I mean, this is just an example. I don't recommend you do this right now. I already have the files ready for you on the Google Drive. They're already there. So, yeah. If you could, let's see how. Let's go back. If you could, I would suggest you download like this folder or maybe the Easy for Me Tutor folder. And once you do, you can see that here on the, oops, sorry, not results, spoiler. Here on the data folder is where you find these let me see. All right, I cannot see.
Yeah, the photon files, yeah.
Yeah, but yeah, once you query the data, the things you want to get are the photon files. It's going to return to you a bunch of files depending on the time range you're looking at. So you're going to have, for example, those that end with a pH. Those are the photon files. Basically, Fermi counts. Each photon that arrives in it, that it intercepts, it counts. It saves on a big, gigantic feeds table. And that's what we use to do the analysis. But we also need that second one, the SC, the one that ends with the SC00 fits. That's what we call the spacecraft file. And that's why you need to have the spacecraft data selected when you download it. Yeah, the spacecraft file basically tells you it carries information about the orientation of the Fermi spacecraft in orbit, right? the Fermi spacecraft, it's flying around in orbit and it's changing orientation on the sky constantly. And that information is saved on in the spacecraft file. So we need both of these to make it work, to make our analysis work. All right, what else? One other thing we need to do an analysis of Fermi data is these diffuse background models. So when we look at a region of the sky, we're not really looking only at the source we are interested in. There's a bunch of photons coming from any direction, and we need to model what we believe these photons are coming from. If they're coming from the galaxy itself, or if they're coming from some extragalactic sources that are not what we are interested in. And these models, they are given by the Fermi collaboration. They're always being updated, and these are what these are. These two. This GLL is the Galactic Interstellar Emission. You can see this image that I have in the background is a black and white picture of the gamma ray sky, and you can see there's this diffuse. You can see the galaxy in bright in gamma rays, and you need to model that, and that's what this file represents. This other file, it's the isotropic template. It's basically, we assume extragalactic gamma ray emission is sort of isotropic, so that's sort of what that file represents. So we need both of these. And let me just, okay. But again, you don't need to, I'm giving you the links here just for completeness, and these links are all also here if you want to read through the file, the text file. But they are also in the Google Drive that I sent you. These are the photon and spacecraft files. They are in the data folder. And here we have a separate folder just for diffuse galactic and isotropic emissions. It's good to keep them here. These ones you only need to download once, and once you have them, you can do whatever analysis you want. The photon files, on the other hand, they depend on the date that you want to observe, right? So whenever you querying for data and you want to observe a source in a given time, you have to download new photon files, new spacecraft files, unless you want to download the whole Fermi data, which is like more than 15 years of data at this point. But I don't think you want to do that right now. Okay.
Yeah, and these diffuse and background models, they are revisited every few years, I think, by Fermi. That's why you don't need to download them every time, because now we are using the PAS-8, and maybe in some years Fermi will update it to the PAS-9.
Cool. So
I'm coming.
Does anyone have a question?
Wait, I'm coming.
Douglas, can we make all the experiments on the Google Colab?
On Google Colab?
Yeah.
I mean, I guess you could, but I don't know how to do that, to be honest. So.
Because I have problem to install the last line, and I tried to do it on Google Colab, so all the packages was installed. So
really?
Yeah, on the cloud. So I don't know if the other steps of the tasks could be done that. So that's what I'm asking. Can we make that in the cloud? So?
I think it would be nice if you could. I don't know how to do that. Yeah, I'm sorry. But if it works, it works.
I install EasyFermi. Okay.
Yeah.
Okay.
Well, once you do all of these steps, you can check if EasyFermi, if everything is working by doing this. You need IPython, so you just use IPython, and then you try import EasyFermi. And once you do that, this window should pop up. So if this works, your installation of EasyFermi went correctly, hopefully. So I'm gonna ask again. Who managed to install EasyFermi here? Raise your hands, don't be shy. All right, not a lot of people. Who managed to create the environment, the first line? Who managed to pass that? Wow, not a lot of people indeed. Yeah, I think so.
Yeah.
It's tricky, right?
Yeah. We should have done this at home.
Yeah, I should have warned you guys
But
yesterday.
yeah.
All right, let me go back. You do an IPython, and then just that's gonna open up like a Python window for you, and then you just do an import easy for me just like you would in Python, and that should open this window. Okay, I guess I'm gonna move along because yeah, we don't have much time. So just to show what the rest of the analysis looks like, hopefully you guys can can read these slides at home, read the instructions at home. If you have problems also, uh, visit Hanieri's GitHub page, and these instructions are there too. But yeah, I guess it's better if we move on. Maybe we can get it working as I try to explain the rest of the thing. All right, so the target here that I chose for the hands-on session is that Blazor, PKS, ta-na-na-na-na. It's a Blazor sitting at right shift, and you're gonna observe them between, yeah, we're gonna observe it for like the first 3 months of the pandemic. I don't know why I chose that. I guess I was bored. I was not doing much during the pandemic, so I just wanted to see what this Blazor was doing during the first 3 months of pandemic. And so this is the time interval. And if you look here, unfortunately, you cannot. Some maybe you can, but I have problems just throwing like the dates, the observation dates on the query. Where is it? Yeah, because when you query, you have choices to like query different types of. Oh my God, where is it? Right, you have different choices. And I show them up here. These are the different time time formats that you can use to do your query. All right, but let's move on. Just so you know, this information is all in the text file. So if you have problems, just go give it a read. All right, what else? Yeah, I thought this was also an interesting Blazor because there are some paper. It is a very high energy emitter, and as Alicia said on her previous talk on gamma rays, uh, there's a lot of discussion, interesting discussions that we can have to explain the very high energy emission of these objects, blazars. Discussions about do they emit from leptonic processes or hadronic processes. So I thought it would be interesting just to try to create if you can manage to create an SED. So let's see if you can do that. Once you have downloaded the files that I sent to you on the Google Drive, uh, remember that being well organized pays off. So it's good to have everything on the right folder. All right, so let's try running Easy for Me now. Once, if you manage to get Easy for Me working, the way to do it, once you have it, as I said, I need to get into the environment that you installed. Uh, the instructions actually call the environment Fermi, but I already have an environment called Fermi, so I just called this one Fermi Pi. Oh, please don't be alarmed, it's just a name. And once you activate the environment, you can just do IPython and there you go, and then just import Easy Fermi. And it should open up that very window.
Technology is not
It's
our
not
friend
on our
today.
side. Oh boy.
Yeah, maybe we are too many connected.
Just a moment. My computer is a bit slow too, so
Yeah.
that doesn't help.
But yeah, more or less you have been following the steps, no? So once you have installed, you activate your environment.
There you go.
Okay.
Yeah, you activate the environment.
Then you do IPython and then import
Oh
Easy
boy.
Fermi.
Oh, I shouldn't do that. Why is it so difficult? All right, let's see here. Let me bring it down here so I can see. All right, so this is easy for me. It's a pleasure for, I hope it's a pleasure for you guys to meet, if it's not too much trouble. And the things you need to set up your analysis, I mean, easy for me is a great tool for like quick analyses of Fermi data. Uh, and let's show what that looks like. What we need basically, oh my God, let's start with let's move it over here. We need the coordinates first. So let me grab it. You grab that, just paste it in there. That's the time range you want to analyze. This Blazar, it's already cataloged. It's already present on the Formi catalogs, so we can just set it. We can just leave it as yes. But if your source was not cataloged, if you're looking at maybe something faint that has not been picked up by Fermi yet, you can come here and say no, and you can name your target whatever you want, and just set it here. But here we are looking at a known object, so we're gonna leave it like that. All right, so what are these? These are the directories and the files that we need, the ones you hopefully downloaded. And you need to tell EasyFormia where these are. So what is this? This is a spacecraft file, right? So we click on it, and it's gonna open another window. EasyFormia, where is it? Oh my God. I think it's this one. Yeah, PKS. And then the spacecraft file is on the data folder. It's this one. And then you just select it, and there we go. It's the one that ends with SC for spacecraft. And you also need to do the same for the photon files. Well, actually, you only need to give the directory for the photon files because usually analysis, they might have different numbers of files. Oh my God, this is so difficult. PKS data. All right, and this is the folder where the photon files are. And you also need to set up the, what is this?
The diffuse.
The diffuse,
the
right.
background.
You need to specify where the diffuse folder is. The folder where you set up where you left your diffuse models. Cool. Oh, this is gonna be impossible because you need to set up the date and I cannot see it from here. All right, I can see now. It's very important that you set up your date correctly. So it's from 2020, midnight.
Yeah, you have to put exactly the same date and times that you use for your query, okay? If not, you might get some trouble.
If you have doubts, I just set it up here. It's very useful to being well organized and have all the information you need centralized so you know where to look for it. All right, so it's 2020, 0000, and then it's 605, right? I think this is it. Yeah.
Yeah.
Cool. All right, so that's set up. So next, the next thing you need to do is to set up where you want your results to be thrown in. So it's good to have a result folder as well, so you know where to look for. And here, EasyFormia, it's quite straightforward. It has some flexibility, and you can choose what you want to do. I think today we will just try to do a simple SED, but you could maybe do a light curve if you want, see how the source varies in time. But you have to remember that you have to specify the number of bins for this type of for light curves and SEDs, right? So you need to make some math just to know the time interval of your bins. I don't think we're gonna want to do a light curve because that takes a while. There are some other options, but I wouldn't recommend you change it right now. You could try maybe doing some extended analysis, and you can model your sources as a disk or as a 2D Gaussian and things like that. But we're not going to do this right now because it takes a while too.
Yeah. And yeah, normally you can do that if it's an extended source. If you have a point-like source, maybe it doesn't make much. It's not needed.
Yeah.
Yeah. And then you have to set also your energy range, no?
Yes,
Like,
yes.
yeah.
But I just set it up to the
To
standard.
the,
Let's
exactly.
to the 100 to 300 GV range,
Yeah.
which is usually the best range for Fermi data. So once everything's set up, you can just hit go.
Mm-hmm.
I'll wait. I don't think we want to do this right now because it does take quite a while to compute light curve. It needs to fit. It needs to perform the fit on each time bin, so it does take quite a lot of time. But the SED is relatively quickly, so let's try to do that.
Well, if you want, you can do it, but we will not see, because if not,
Yeah.
we will take. It will take maybe, I don't know, can take 40 minutes.
Yeah,
or more.
probably something like that.
Okay.
Also, one last thing that might be interesting to know is the lifetime cube. Here, I have unchecked the option of computing the lifetime cube. The lifetime cube is sort of a, how do I explain it? It's sort of like a giant table that tells you how much time the Fermi spacecraft spend looking at each position in the sky, each specific position. And calculating the lifetime cube is quite expensive. It might take a whole lot of time. So if you don't have this checked, you need to compute a lifetime cube for your analysis. But hopefully I already did this, so we can just reuse the lifetime cube that I have already used. And that is on the results folder that I shared with you. Oh, don't look at all of these. Where is it?
Yeah.
It's actually in the other results folder.
Because if we were doing it live right now, well, since we are only analyzing few months of data, it might take maybe 15 minutes, 20 minutes. But if you use a lifetime cube, it will save us a lot of minutes right now because he already did that,
Yeah.
you know. So,
Yeah, the lifetime cube is a very heavy quantity. It's very computationally expensive to run, but it's something you need through every analysis. But once you have it, once you're already done your analysis, you can just reuse the same lifetime cube, and that's what we're gonna do. It's I think it's on the results folder. Oh my God.
it is.
Yeah, so you guys can do that. Yeah. Hopefully everything is set up. We're not going to do the light curve right now. So let me just press go. Hopefully everything will work out fine. And you can see the terminal. It checks. It's good to have the terminal open because if you have any bugs, any problems, the terminal will tell you that you had a problem. Here it didn't, so it gives you some warnings. I don't think that's really relevant, so let's ignore that. I think we can just ignore that. But if there are problems, the terminal will tell you, and FermiPy will not, unfortunately. FermiPy will give you a few hints of what it's doing. So you can see like it's using a pre-computed lifetime cube. So that's what we were talking about. We already have a lifetime cube. Let's not compute it again. It takes a long time. And yeah, it's gonna take a while.
But if you guys are bored, you can calculate your own lifetime cube. So
let me just show you now. Oh no, my computer froze. Yeah, my computer is very slow. I better not mess with it while it's running.
And as we were saying, because if not, you would have to use all of the steps following the Fermi-Lat analysis that instead of taking, I don't know, we have loaded everything here in 5 minutes, or we had taken 10 because we have been a bit slower. But if not, the Fermi-Lat analysis, it takes a bit longer because you have to do all of these steps and it takes a little bit more.
Ah, that's great.
Okay, it's not working. Of course.
Let's wait, who knows? Hopefully you guys don't have that problem.
Yeah.
All right, so where are you on these steps? Did you manage to install EasyFermi? Did you manage to open the window? Raise your hand if you managed to get EasyFermi working. Yeah, the same people. Right. If you have some questions, I guess we're waiting for it to go. If you have some questions.
Yeah. Well, anyway, as you can imagine, it's a bit difficult in 40 minutes, 45 minutes to try to set up this and that it works and that we all manage to do it. But if you are curious, just remember that always in this GitHub website that is put there is a lot of information. And actually you have these YouTube tutorials by Raniere that are very, very, very useful. Ah, it's doing something. Yeah.
Oh, there we go.
Yeah. Okay. So,
It seems
so
so
yeah, and
pretty
if
cool.
you have a bit more time, you can of course calculate the light curve and the TS map, and yeah, and be aware that depending on the amount of data that you download, it will really take a long time. If you by any chance want to analyze 15 years of data, it will take a super long time. Yesterday in the first folder that we sent you, we were collecting 1 year of data, and it was taking more than an hour just to calculate this LT cube. So.
All right, hopefully you can see. Oh, I shouldn't have maximized the window. Now I can minimize it. But I set it to spit out the results in here. Let's see if it's what it's doing. All right, there's a lot of stuff here that I already used. I thought God damn it. Now I can't. Well, if you manage to do it, you can look on your results folder. This is after the whole analysis has been done. It spits out a bunch of files. You don't need to know what what all of these are, but it's good. Look, it's doing
it's generating stuff. Yeah.
Yeah. But one of the data products from this analysis are the count maps for this region of the sky. Let's see if I can open it. Maybe I can't open it. There we go.
There it is.
Yeah, once you manage to run everything, one of the data products is the count map. So I think it's really interesting that look at this region of the sky. The color tells you how many photons you got from that region. And yeah, most of the gamma ray sky you'll notice is very dark, but hopefully we're looking at a blazar. So in a very short interval, short amount of time, which is about 2 months that we're looking at, it spit out a bunch of photons. So we can detect it with a very high confidence. Mm-hmm. What else? You can see here fits to the counts as a function of galactic longitude and galactic latitude. So you can use these types of diagnostic plots to have a good visual intuition on if you actually manage to fit it correctly. Mm-hmm. Here we have some points, but overall, the target we are interested in is right in the middle of our ROI, our region of interest. Mm-hmm. So it seems that we are fitting that well.
Yeah, and it just generated the spectrum. It just appeared there.
Cool.
New one.
I'll show that real quick. But yeah, just for completeness, this is another diagnostic plot, and it tells you how much each of these sources in your region of interest are contributing as a function of energy for photons for your ROI. Mm-hmm.
Yeah, because it identifies the sources that are in the field of view, no, from this catalog that we were mentioning earlier, right?
Yes, exactly. Yeah, I should have said that. Mm-hmm. These are all sources that are known already. These are gamma ray sources that the Fermi collaboration has already cataloged, and they are in the Fermi catalog. So Easy Fermi already knows that and uses the catalog to do the analyses. So yeah, maybe if you want to explore new, potentially weak sources that are not on the Fermi catalog, that might be a little more tricky, but you can use Easy Fermi as well. Just tag that non-cataloged box there. It's practically done. That's great. And it seems that we don't have any problems. Mm-hmm. Let's see, what else? All right, so the data products are here. Oh yeah, just so here a comparison. This is our data, right? This is what Fermi sees. These are all the photons that it captures in the time interval we specified. And this is the modeling, let's say the best fit model for that region of the sky. So you can see sort of a visual representation of what Fermi what Fermi 2 believes is the best representation of that region. And yeah, this is what we call a TS map, a test statistics map. It tells you basically where the color represents like sort of a significance of how much it believes there is a source at that location. So you can see we're looking at a blazar integrating with just 2 months of data, and it's super, super bright, whereas other regions of the sky are less bright, and they correspond to lower significances to having a source there. So that's specifically useful, most useful for like when you don't have, when you're not sure you're going to have a detection. It's good to look at your TS maps. These are very important. And yeah, this is our SED. This is what we managed to do. How pretty! It seems that we have not reached the peak in energy, right? But that might be due to the limited amount of data that we got. We're just looking at 2 months again. I did do this analysis using more time. Let's see if I can show that. Oh my God, it's so difficult. All right. I think it's in here. I used a little, no. No. Can you guys see an SED? No.
No. Huh?
Oh boy. Oh, what happened? No. Don't do that to me.
It's not in the results folder, no.
What is this? Is this light curve? I think yeah, okay. We didn't do a light curve here, but I did it at home. So this just so you can see. This is a light curve spanning, I think, 3 months. Yeah, and yeah, Easy Fermi gives you a light curve. If you want, you're gonna get something that looks a bit like this, and you can like study the variability of your source. You can do it. It gives you both an energy flux light curve or just a regular photon flux, whatever floats your boat. Yeah. And one last thing, it's the spectral. A whole bunch of information about your target is gonna be given in this TXT file that EasyFermi also spits out. And here you can see. Let me see. Here are basic information about your source, like its coordinates. You can see like TS, the confidence at which you detect it. We have around a TS of 300, so that's very, very high confidence. And there's spectral information. There's the flux that we managed to get, and the spectral parameters. If you want to fit this again, EasyFermi also spits out like fits files for the SED, for the modeling that you did. And so if you want to reproduce this again, you can open up these files, you can explore, play around, and the spectral parameters are given on this TXT file that EasyFermi gives to you.
So,
all right.
Yeah, so I think we have to move on with Irene, but yeah, as you can see, actually, I mean, once it works, it's pretty easy to use because these guys have done a very friendly interface. So play at home if you like to do some Fermi-Lat analysis and maybe learn a little bit how this works. Maybe this gets you also to be familiar with then doing some more complicated Fermi-Lat analysis. And I think we should thank Douglas for his amazing work.
late. Sorry, I'm cutting off the questions because we are running super late, and we can do it in coffee break, okay? All right, so thank you. Alicia, Irene. And now for something completely different. This one? Yes.
It doesn't work. Can I have a bit of help, please? And really? So I cannot play with that?
No, you can. You just need a mirror. Let's open the.
No, I wanted to show first a couple of slides, but come on. Is it not possible to play it like that? No, that's so cool. Can I connect with, I don't know, Zoom and show it directly?
It doesn't show because it's a secondary screen. Oh, wait.
If you do control F6 or something like that?
There you go.
Oh, okay.
This one here. Screen. Here. So they're both in there.
Great.
You're gonna be like this other guy. You wanna put
Yeah.
this here so you turn around?
No, then I don't see the mouse anymore. Ah. Sorry. Again, no. No, it's fine. So, sorry for the mess. So what I wanted just to say is that we have, as we discussed few times already, there is an entire interface that you will see in a second that gives us access to all the data that we want to download if you want to play with them. So I will leave the presentation done from this colleague available, and you have all the places in which you can download the data from a single event, from a catalog. You can choose different things. You can do really an enormous amount of things. Let's see if I can show you at least a couple of these pages. So the interface now is slightly different, but the interesting information on here. So you have the data, and you can download the data, and so you have to choose what you want. If you want the catalog, if you want the single event. Sorry, it's quite uncomfortable to say like that. This is event and catalog, so you have both the information, and then you go on release, and then you have everything you need to know, anything. So let's see if I can go back, close this. I will put it available so it is fine. Okay. So if you want to play a bit with the waveform, what we can do is to go to this website, gwosc.org. If you connect, you will have a screen like that. Then, if I manage to show you, if you go here, Open Data Workshop, you end up in a page like this. Okay, are you able to connect? Okay, go. Then, since we just have done an hands-on session of few days, that was a fortunate case. So you go here, workshop, and you open another browser, or you can do whatever. Then you have to click on register for free. Okay, and you have to enroll. So sign up with anything that you prefer, Google, Facebook, whatever. It's fine, LinkedIn. And eventually you will arrive to something that is like this. So let me know when you are there so that we can move on. Did you miss any step? Should I repeat the... Okay, so let's see. gwosc.org, okay? Then Open Data Workshop, this one in the middle. And so you end up in this page. You click on the latest one, Workshop, Graduation Wave Open Data Workshop number 6. And you have to scroll and register for free, okay? And then you have again another page in which you have to choose one of your emails, Google, Facebook, LinkedIn, whatever, and you can get in, sign up, and you arrive to a page like this. Of course, I was already enrolled, but you should not have that red line. You there? Not at all? Okay. Is somebody having a problem? Okay. So if you open this one, the Open Data Workshop number 6, that will open up a page that is like this, okay? So here you have plenty of different things to play with. Everything is really well described, and so you can open and play with it. I just want to show you a few of them, just to connect it to what we have seen. So if you scroll down and you go, oops, that wasn't a good idea, on generating waveforms, okay, there should be tutorial 1.4, okay? When you open it, you click on the tutorial and you launch in Colab so you can do it online directly without any issue, okay? Every page is done almost the same way. So you scroll down, and the only thing you have to do is to remove this hash mark at the beginning to see how it works. And then you click here. Oops, what I've done. Okay. Yes, run anyway. Don't worry, nothing will burn. Okay. So when it's done, you will have a green flag nearby the arrow that you have over there. Okay, preparing data. Let's see. That's because I choose to show you how to to change the masses in the waveform. That's he has to load a bit of data. Okay, so done. Okay, so you go here and you have to initialize the code that is a Python code. SpicyBC is one of the most used one, okay? That was done. And then here what it does, sorry, but, okay, so what you choose here is the particular kind of waveform that is this one, IMR phenon D, that is one of the most stable one. And you see here the masses that we are simulated an equal mass waveform, okay? 10 solar masses, that's the time and that's the lower frequency, 30 Hz. And that what we should see, it's a plot with the two different polarization, the plus and the cross, okay? So you scroll down, maybe I should make it. Okay, it's done. And this is the plot, maybe. Okay, so this is an equal mass binary black hole of 10 solar masses. What if I want to have a really asymmetric signal, so 100 instead? Let's see what happened. So I have a huge black hole and one that is tiny. See? The waveform is completely different. Okay? And we just change one of the two masses. Let's see what else we can change. So that's over time. Sorry? So this is the zoom, you see? Yeah, the scale of the time has been, the 0 is the merger time, so it's been rescaled. And see now you see also is a zoom nearby this frequency. So it's between minus 0.1 and plus 0.1, okay? It's a zoom in of the previous one. It's not? Yes, you're right. Because it's completely asymmetric. Yes, exactly. So this is instead the next plot is you Fourier transform the signal. So you remember that I showed you the sensitivity of the detector, and then on top superimpose how long the different signal we stay in the sensitivity band. And that's exactly this plot, without the sensitivity of the detector, but with the Fourier transform of the signal. And the two polarization are one on top of the other. So here is still the equal mass. So let's see what happens if I change again the mass and run it again. How different it is. You see? The Fourier transform is shorter, so we stay in the sensitivity band less than the signal that has equal mass. Okay? Okay, let's go through that. Okay, here instead what you have is you see how the length of the waveform increases at a certain distance. You see? So you have the plot in which you have again the strain and the time, but what you have again the equal mass, so 10 solar masses and 10 solar masses, but you are injected at different distances. These are megaparsec, so 5 megaparsec to 100 megaparsec. Let's see what happens if, sorry, come on, go down. Okay, let's see if we change the distance here. Let's put a factor of distance. in megaparsec. The mass are here are exactly the same as the previous one. That's distant. Ah, no. Sorry. I cannot see. I cannot see, sorry. No, that's distance. Yes. No, because the mass is mass 1 and 2 equals to m, and m is the previous one. So that's distance. Wait a second. Maybe like this. Is this one the distance that I was looking at? Sorry, you're right, that's mass. So what I change here, sorry, you were right. What I change here is the mass again of the different component. And so you have this one that is 50 solar masses. This is an equal mass of an equal system. Can you still hear me? Okay. That is 100. This is 300, and this is equal to the orange one. Okay. Now what I wanted to show you is this. Okay. So that's the one I wanted to show you. Maybe. Okay. So this is the waveform of an equal mass binary black hole with different distances. So you see they are going from 100 megaparsec to 1000 megaparsec. So let's, come on, let's change. Okay, let's try. So I want the system of that is really asymmetric, and I want to have something closer. Let's see. Oh, let's do it first in this way, and then we change the distance. You see, that's how the waveform changes with the different mass ratio. Let's see if we, with the same, okay, with the same mass, so 110, we change also the distance. Yeah, so what it does, yeah. Let's see. So it's slightly different compared to the previous one. Anyway, sorry, I'm getting a... Yes. And I cannot read anymore. Okay, so at the end of... So for each of these pages, you have also the video. You have this part is a tutorial. So each of the plot is explained, and you can actively change whatever you want. And at the end of each page, there is an exercise that you can have. So in this case, what it's telling you is to do the same exercise with the binary neutral star. So what you have to remember or go to find are the information related to the mass, the information related to the distance, and you can just copy and paste the part of the code, or just act like I was acting changing the masses. So the binary neutron star was 1.46 solar masses and 1.27 solar masses. And so you can plug in the value and see how the waveform looks like. And then apart from the exercise, then at the end of each of these tutorials, there is also a quiz, that is a question related to the exercise that you should have done. And so if you get it wrong, it doesn't matter, because it gives you the correct answer with all the explanation and the parameter that you should have been used, okay? So you can go through the different pages. The one that I wanted, this one, for example, I show you briefly. Is showing the time evolution of the Fourier transform. So here you have the GW1707 17, and with this it will load the data corresponding to this event. You will see that at the end of the page it will ask you to do the same exercise with another event, 1904-12. That is one of the unequal mass. And so you just run through the information, change the parameter, and play with it. I think the best way is to learn doing things. So for example, this one, see, there is something wrong here. What is wrong? Yeah, why it's empty? There is something missing. What is missing? Come on, guys. What's missing? So if I show you this plot and this plot, what's missing? The z-axis. See, you don't have colors. And so you cannot discriminate anything. Okay, so if you plug in the correct information, what you have is this type of glitch that shows exactly in the middle of the time frequency plane, exactly like in the case of the GW170817 that you have to remove. At the end of this page, what it does actually is to let you remove some of these glitch. I think it's exactly that one. So this one, where is it? Sorry. So these one are the data from H1, so Hanford. And you see, this is the time frequency plot. You don't actually see anything apart from these, that is really faint. Then what you do is you scale a little bit, so it gets a bit better, and you rescale the time. 0 usually is the merging time. So from there you go back in time, and so you have negative time. And this you put the y scale in log, and you normalize the energy, okay? And there is a zoom in the energy. Before was till 30, and now is till 17.5. And what you have here is the log and normalized energy. This should be the other one. Where is the detector? Yeah, that's a different time, you're right. Okay, these are instead the segment, so the data from Livingston L1. Okay, and so you see, you should remember that we have seen that glitch. And so you can see that in the Livingston detector with the GW170817. And so what it does in the following one is to have exactly the, okay, the zoom in, you reset the time and you make a better scale of the x-axis, and so that's exactly the time frequency plot that I showed you the other day. And then what you do, maybe later on, is to remove the glitch. You see? What you see is just you blacked out that part of the glitch. And so when you do that, what we said is that you have to remake the analysis because the alert on the Livingston detector didn't work due to the glitch. And so that's the challenge that wants for you to take another event and do exactly the same. So also in this case, you will find a glitch, then you have to constrain the glitch, and so remove the glitch at that time in the parameter space, so it will be removed like in that case, and you will have exactly the time frequency plot that we have seen. Okay? So I think I can stop here, but you have plenty of these. Let me show you. So at the end of this, see, this is the tutorial. Then you have the question. So, I answered already, sorry. Okay, no, I wanted to show you that if you, no, okay, let's take one that probably I didn't see. Okay, acquits, whatever. We make a random choice that we suppose is, no, of course is correct. Okay, sorry. Sorry. So when you get the wrong answer, it doesn't matter because what it does is just saying this is incorrect. The correct one is B. In this case, it's easy, but usually when you have to plug in and make the different plots, it shows you also the plot that you should have been used. So it's pretty straightforward, and I think it's nice when you want to play around.